In this session, we're going to be looking at how translation software works, in particular how an interpreter can execute programs without producing a translated version. And we're also going to be looking at the different stages in the compilation of a program if you use a compiler. So far, we've just been talking about how operating systems manage memory and processors and how the hardware actually works. But when you're actually creating a program, that program is written in a high-level language. And that's the language that you perhaps understand, and that's how you explain logic. But that program needs to be translated into the actual machine code, which would be different for different devices. So we use these programs or these intermediate programs, which are called translators, basically two main ones, interpreters or compilers, and we're going to be looking at how these operate today. Now, before we begin, it's useful for you to understand some key terms. So do pause the video and jot these down. We're going to start off with lexical analysis, which is the first stage in the process of compilation. Here, you remove unnecessary characters and tokenize a program. We then move on to syntax analysis, where we check the grammatical side of things. This is the second stage of the process. Then we generate code, which is pretty straightforward, and then we optimize that code, and that's the fourth stage. Now, later on, in perhaps the next lesson, we're going to be looking at BNF, which is the Backus-Naur form, and this is a formal method of defining grammatical rules of a programming language. So how do you understand that the keywords are actually correct? And that's where BNF comes in. And syntax diagrams are the graphical equivalent of BNF. And finally, we have reverse Polish notation, which is a method of representing arithmetic expressions without the use of brackets or special punctuation. So hopefully you've got these key terms down. Let's begin with the lesson. So how does an interpreter differ from a compiler? Well, chances are that if you studied IGCSE computer science, you would know the answer of this somehow. An interpreter executes the program it is interpreting. Every line is executed. A compiler does not execute the program it is compiling. With a compiler, the program source code is input, and either the object code of the program is generated or an error message is output saying that there is some error in your source code. An interpreter will just execute it line by line and either give you the results or an error message. Now, once the compiler produces this object code can be executed without any need of recompilation. And that's different from an interpreter because every line would need to be present if you want to execute it. And so you need to have an interpreter being used every single time you want to run that program. Now on screen you've got two diagrams. One shows you how a compiler uses source code. So it takes the source code, it either gives you error messages or the object code. You do not execute any source code statement here. The object code is executed. And for an interpreter, you get the source code. Sometimes you might have error corrections made as a result of error messages that are output. And you might also include program input into the interpreter to move on to the next line of the code. And the program output is also displayed. So you're actually interacting with a live version of the source code rather than a compiled version of the source code, which is known as the object code. So hopefully that makes it clear. One takes the source code and executes it line by line. The other one just takes the whole source code and creates object code or gives you an error message. Now, both a compiler and an interpreter will have to construct something called a symbol table because, say for example, you have a keyword like print. That print needs to be translated into something called a token, and a token is a number. And the reason we need to convert it into a number is because eventually everything needs to go into binary. So think of this as kind of like using an ASCII or Unicode table to translate text. Now an interpreter will create a table and allocate space for this in memory because reserved keywords like print will already have a token that's been allocated to it by a programming language, but constants, variables, and other data items that have been used by the program, they will need to be stored as a token. And then the interpreter will check each statement individually and report any errors which can be corrected before the statement is executed. So if print is token number 30 and you typed it incorrectly, the token would be wrong, and then it knows that there's a problem with it. After each statement is executed, control is returned back to the interpreter, so the next statement can be checked before execution. So that symbol table that you see on screen is an example of a small program where you got X, Y, and Z and a couple of input or output statements. And X, Y, and Z's values can change, therefore they're variable type, and those statements are constant because they never change. So each of these variables or constants are given a value 81, 82, 83, 84, and 85, and their data type is stored in the symbols table. A compiler works slightly differently, but it still uses a symbol table, and the process of translating a source program written in a high-level language like Python into object code can be divided into 4 stages. We go through lexical analysis, syntax analysis, we generate code, and we then optimize the code to make sure that it is efficient. So the diagram on the right-hand side probably will make more sense because it's linear. You take the source program, it goes through lexical analysis, it goes through syntax analysis, and then it will go through semantic analysis. Now we don't need to know about semantic analysis for the syllabus, so we're not going to cover that part. That allows us to generate an intermediate code, and that's where perhaps the interpreter might stop. The code generation stage is when you translate that intermediate language into machine code, and then you optimize it before you get the final object code. Now on screen you see an example of lexical analysis. We've got a source program which is pretty straightforward to understand. Declare x, y, z, which are in integer form. Output the statement, get the 2 inputs, z is equal to x plus y, then you output the answer. Now at the lexical analysis stage, we're going to remove any unnecessary characters. For example, comment statements, they're not needed. Indentations, which make the program easy to read for the programmer, they're removed. And you might say that, well, that looks pretty close to the original program. And that's okay, because the only unnecessary part in this particular one was the comment statements, and they have been removed. But for complex programs, you're also going to remove indentation and all sorts of other bits. So lexical analysis is the first stage in the process of compilation. And before translation, the source program needs to be converted to tokens, and this is where tokenization comes into play. It is at this stage the interpreter and also the compiler will convert all of those XYZ, the input and output statements, into tokens. Now, in order to tokenize the program, the compiler will use a keyword table that contains all the tokens for the reserved words and symbols used in the programming language. A keyword table is where all the reserved words and symbols are already stored. So print, what does that mean? Int, what does that mean? All of those are stored in the keyword table. You can take data from there and create your symbols table, and then you can assign new values to all the constants and variables and everything else that you've used in the program. Now the keyword table is going to be the same for every program because those keywords are reserved. They've been created by the creator of the programming language, but the symbol table will change depending on the program because it will contain some tokens from the keyword table and some tokens from constants and variables you have used in the actual program. Now on screen you'll see an example of the program that we were trying to work with. The symbol table, which was created because these constants and variables are unique to the program, and then you see an example of the keyboard table, which has the reserved keywords, the operators, and the relevant token. Now, taking data from these parts, we can create the output for the first 4 lines of the program, which look like a series of numbers. So 31 is declare, 81 is X, 04 is a comma, 82 is Y, 04 is a comma again, 83 is Z, and so on. So that entire program, which is in text form basically, is converted into a series of tokens. And these tokens are then used to check for mistakes or grammatical errors in the syntax analysis stage. This process of taking high-level statements and converting them into tokens is called tokenization. These tokens are then taken into the syntax analysis stage and then checked for errors. And this process is called parsing. So parsing is basically where you analyze parts of speech, and we use the same term. So we're going to look at all of these tokens and see if there are any particular mistakes. Now, once you converted text into tokens, this process is a lot more easier than just going through and analyzing the various different forms or the various different combinations of text that might be possible. So the whole program goes through this particular process, and this is where we use the back-as-nor form, where the rules of parsing or the language are actually defined. We'll get to BNF in a bit. However, at this particular point in time, if any errors are found, each statement and the associated error are output. And in the next stage of the compilation, the code generation isn't attempted if an error is found, because you just stop at this stage, you output it to the user, hopefully the user fixes it up. The compilation process will only finish after this stage is completed and after the parsing there are no errors. So if the tokenized code is now error-free, it will then be passed to the next stage of compilation where you generate the object code. In the code generation stage, the object code is the main goal, and the program needs to be syntactically correct for an object program to be produced. And then this machine-readable form of code is generated. At this particular point in time, the code can no longer be read by humans. It's in a form which only the machine can understand. Now, the object program can be in machine code that can be executed by the CPU, or it can also be translated into an intermediate form that is converted to machine code when the program is loaded. Now, think about it this way. You write a high-level Python program, and instead of generating the object code, which will only run on the machine that you're currently on, you create intermediate code. And this intermediate code can then be taken to different machines and compiled into that machine-specific object code. You might argue, well, why not just use the source code? Well, the fact is that you've already processed two stages of the compilation process, so you've kind of got an intermediate stage. So the compilation process is a lot more quicker compared to going back to the high-level language and then converting it and going through the motions again. Now, this allows greater flexibility, and for the exam, you need to know the benefits of intermediate code, and they include the use of relocatable code, so the program can be stored anywhere in main memory, the addition of library routines to the code at this stage to minimize the size of the stored object program. That can happen as well. The linking of several programs to run together is also possible at the intermediate code stage. Remember, once you've generated object code, you can't do any of this. So that's final. So at this particular point in time, you could daisy chain, or you can link a few programs together, a few library routines together, and still get away with it. But you won't be able to do that once the object code is generated. The next stage after this is optimization, and this stage supports the creation of efficient object program. So we've created the code, but then there are going to be repeated patterns in there which the compiler can identify and then reduce to save time, storage space, memory, and CPU use. Now, this optimization can take place after the syntax analysis and the code generation stages are completed. The optimization only works if two lines of code are together and in an order in the program. So if you've got different parts of the programs which might be repeated, that can be very tricky to identify. Task of code optimization is often one of the most challenging stages of compilation, and not every compiler is able to optimize the code that's produced for every source program. However, there are possibilities within code that can be optimized. Now, there's an example on screen which highlights this really well. You've got some original code which says w is equal to x plus y, v is equal to x plus y plus z. Now, when we compile it, we get load x, add y, store w, load x, add y, add z, and then store the value in v. Now, you can probably see that x plus y is being repeated in the code. Now, in the optimized code, you will still have the same thing, w is equal to x plus y, but instead of saying v is equal to x plus y plus z, you simply say v is equal to w plus z, because w is already x plus y. Now, this leads to a reduced number of lines of code, which means the code is optimized. It'll do exactly the same thing, just faster, and save storage space. Less space in memory is required, and the CPU has to operate a smaller number of clock cycles. Okay, that's where we're going to draw the line for today. Hopefully you understand what the 4 stages of compilation are. You should be able to articulate what happens during the lexical analysis stage, what the process of tokenization is all about, what happens during syntax analysis, what happens during code generation, what is meant by intermediate code and the benefits of that, and what is the purpose of optimization. If you do have any questions about this, as usual, get back to me. Otherwise, I'll see you in the next lesson.